Right. So we are discussing periodic classification. As long as, it might, it will take time to finish the chapter, but every time I wanted to remind you, and I would love to remind you that, this chapter is not about, putting the elements in rows and columns. I always remind you. Because the degree of seriousness is required, because I'm not giving you around 120 odd elements to you to place them in rows and columns. It's not like that. Remember two things. One, there are schemes, right? There are rules, there are principles which drive the periodic table. You must understand. That's number one. Number two, each period, when you view it as a shell, right, and you have infinite number of shells in a period, in an atom, because the principal quantum number values which are designated to shells vary from n is equal to 1 to n is equal to infinity. So you have infinite number of shells in an atom. So if each period is regarded as a shell, you must be having infinite number of period. But what is very strange is till now we are unable to complete the 7th period itself. Right? So it leaves a scope for you to go out, venture out, discover an element, and then I have a place for you in the periodic table. You must understand that, right? And also the second point which I would like to tell you is, there are some properties which repeat itself at regular intervals. And those properties are nothing but what? The periodic properties which we were discussing. And the most fundamental thing yesterday we started off for the periodic properties is basically atomic radii. Because the physical and chemical properties of an element boil down to atomic radii, you must understand. So every physical, chemical property, which I call it to be a mode of activity of an element, is basically a function of atomic radii. That means that in simple words, to understand why each and every element behaves differently with respect to physical and chemical properties, the 120 odd elements, then the answer is simple. The answer is simple basically. It's nothing but what? Atomic radii which is playing a role, you must understand here. Right? So atomic radii is the only fundamental things on which the periodic properties depend. If you remember, we were discussing electropositivity, electronegativity, you were discussing electron affinity and ionization potential. If you look into this, all these periodic properties which repeat themselves at regular intervals are all functions of what? Atomic radii, you must understand. They are all functions of atomic radii, right? So the most fundamental thing, and hence the modern periodic law also says that the mode of activity of all the elements in the periodic table must be a function of what? Atomic radii. Such significance is given to what? Atomic radii, you must understand. So even we were discussing about ionization potential yesterday. Ionization potential. Now you must understand that ionization potential is also a periodic property which will be repeating itself at regular intervals. And I was telling you even ionization potential is a function of what? Size. And then we are going in for the trend, and in a periods the IP increases, and in the groups the IP is decreasing. This I was discussing. And one of the major factors when during the investigation what we found was shielding effect was playing a role for what? Ionization potential. Now what is shielding effect? If you remember in the last lecture, I just wanted to brief you. Shielding effect, what is it? If in between a nucleus, if in between a nucleus and the outermost shell, if in between a nucleus and the outermost shell, if the number of shells increase, then the nuclear force of attraction that falls on the outermost shell decreases. When the nuclear force of attraction on the outermost shell decreases, then the outermost shell tends to relax, because you're not attracted towards the nucleus as much as you want. So if the outermost shell is relaxing, it's easy for you to spend less energy and remove the electron or extricate the electron, thereby the ionization potential falls, you must understand. So I was actually telling you that ionization potential is inversely related to shielding effect. You must understand. This is, ionization potential is inversely related to what? Shielding effect, you must understand here. So what I mean is, greater the shielding effect, lesser is what? Ionization potential. Now also regarding shielding effect, now look into the definition properly. What I'm telling, it's between the nucleus, see what I'm telling, between the nucleus and outer shell. Between the nucleus and the outermost shell. It's all about between nucleus and the outermost shell. We are just interested in the outermost shell because it is only the outermost shell which will participate in what? The bonding. As a chemist, I'm more interested towards outermost shell. So between nucleus and the outermost shell, if number of shells increase, right, between nucleus and the outermost shell, if the number of shells go on what? Increase, then effective nuclear force of attraction, right, actually decreases. It actually decreases, you must understand, right? So between nucleus and the outermost shell, if the number of shells increase, then the effective nuclear force of attraction on the outermost shell basically decreases. When I say effective in the sense, it is a resultant, the consequence of having greater number of shells between nucleus and the outermost shell. Come on, I have not finished here. Rather decreases, this is true, and also the trend of shielding effect, also the trend of what? Shielding effect, if you see, S is a better shielder compared to P, compared to D, compared to what? F. You must understand. That is a trend what we have discussed yesterday. That means between nucleus and the outermost shell, if the more bulk of the electrons are added to what? S, the bulk of the electrons are added to S, they are better shielders. If it in between the nucleus and the outermost shell, if the bulk of the electrons are added to P, then it is also a better shielder. S and P, it is also a better shielder. But coming to D and F, right, if the bulk of the electrons are added to D and F between the nucleus and the outermost shell, they are very bad shielders. In fact, F has a we call the shape of F to be a peculiar diffused shape. Look into this. Like the F is described like this. F shape, if someone is asking, what is the shape of what? F. It has a peculiar diffused shapes. It's a peculiar diffused shapes. That means that it doesn't know the shape of F. No one knows the shapes of F. They call it to be peculiar diffuse shapes, indicating that the F orbital, which is eightfold degenerate, has some pores in it. You must understand. So when you have pores in it, I think the nuclear force of attraction will be penetrating through the F and then falls on the outermost shell, where the outermost shell is slightly pulled inwards. Pulled what? Inwards. When it is pulled inwards, I think it would be difficult for you to remove what? An electron. You must understand. That's why the shielding effect is varying in S, P, D and F. So what I mean is the S orbital is symmetrical around the nucleus. That means it's spread over very nicely around the nucleus, right? And then I think it's a better shielder. And P, D and F have directions. So they're basically shielding, and you find the density of electron in a particular direction. So directional orbitals P, D and F are not good shielders. You must understand this, right? S doesn't have direction, so it's a better shielder. So the trend of shielding effect, if you see S, P, D and F, I think F has the least shielding effect because it has a very peculiar diffused shapes. That's how I describe F. You also remember, if someone is asking you what is the shape of F, it has a very peculiar diffused shape, indicating that the way we describe the F orbital is basically indicating that they don't know the shape of F. S is spherical, P is dumbbell, D is double dumbbell. What is F? We don't know. We do not know the shape of F orbital. Right? Now, why we do not know? You understand that, to get the shape of an F orbital, you need to get an energy of the radiation that matches with the F orbital, which is very high. For the simple reason because F orbitals come into play only from the 6th and the 7th periods. You must understand. 6th and the 7th, I think the energy levels are higher. And if you try to get a photograph using a radiation of an electron which is present in the f orbital, then I think instead of giving you a photograph, the electron will be kicked out and you will never get a photograph of what? F. That's why people do not know the shape of what? F orbital. Hence they call it to be something like a peculiar diffused shapes. Peculiar diffused shapes. That means that the f orbital is having some pores and the nuclear force of attraction actually penetrates through the pores and then falls on what? The outermost shell, and thereby the outermost shell is basically pulled inwards. Thereby, I think you are not shielding well. When the outermost shell is pulled inwards, then it would be difficult for you to remove the electron from the nucleus. Thereby the ionization potential increases. So sweeping statement, if you wanted to make, what are we doing is we are trying to investigate what is the effect of shielding on ionization potential. First of all, the sweeping statement would be greater the shielding effect, lesser is what? Ionization potential. You must understand the energy required would be lesser. But if you wanted to go into the trend of shielding effect, is the shielding effect same for all the subshells? Same for all the electrons which are occupying the subshells? Absolutely not. You have varying trend, right? If the bulk of the electrons are added to what? S, you are a better shielder. If the bulk of electrons are added to S and P, still you are a better shielder. But if the bulk of the electrons are added to D and bulk of electrons further added to F, I think they are the worst shielders, and then the ionization potential will increase. That is a total thing you must understand here. Right? You must understand that. That's also one more point. The other point, what I was basically telling is, the outermost shell relaxing and the outermost shell being pulled inwards. Two things are happening. Outermost shell will be relaxing if the bulk of the electrons are added to what? S orbital, whereas the bulk of the electrons, suppose if it is added to what? F, I think it is pulled inwards, right? So the outermost shell being pulled inwards or pushed outwards, it means that the size is also varying. Will that be seen in a group? Yes, of course it is seen in a group, and I was writing this for you. Watch carefully here. Also, if you look into some of the applications, then it is somewhat like this. Also remember and recollect. Remember and recollect. We discussed this. Also remember and recollect. Ionization potential is inversely related to size. And now I'm telling ionization potential is inversely related to shielding effect. Shielding effect, you must understand. So it clearly indicates even shielding effect is directly proportional to size. Greater the shielding effect, the outermost shell is basically relaxing. Relaxing, the size will be increasing. You must understand. Right? If the shielding effect is lesser, right, that means that the outermost shell is basically pulled inwards. So if you, as a mathematics student, you can understand this is how the correlation is. These both are inversely related. So this and this must be directly related. And the consequence is very much there before you, which I would like to write it here. As I told you, down the group, this is asked in exam. This is an examination question. That's an examination question. This chapter is theoretical chapter. So the questions will be theoretical in nature. So you should be very much knowing the concept. Then only you will be in a position to attempt. Right? Here is one theoretical question which I'm putting it before you. Down the group, the size increases. The size basically what? Increases. There is no dispute in it. But what I am telling, the magnitude of increase seen on the top, the magnitude of increase which is seen on the top of a group diminishes down the group. Diminishes down the group. It diminishes down the group. That is the assertion which I am making it for you. So what is the assertion? Down the group the size increases, but the magnitude of increase seen in the top diminishes down the group. And if you look into this, I think the basic reason for this, the basic reason if you actually look into, it's nothing but what? Shielding effect. And once it is shielding effect, it also affects atomic size. You must understand here. Atomic size or atomic radii, that is how it is. If I can describe it to you very quickly, then let us take an example of the first group and go in for the discussion, right? But understand here, these are the gist of what I'm telling. Ionization potential inversely related to size. Ionization potential is inversely related to the shielding effect, and if that is the case, then size and shielding effect are directly related, and the consequence is very much there before you. And down the group, the size is increasing. No disputing on that. Any group you take, the size will increase. But the magnitude of increase which you see it on the top actually diminishes down the group. And the reason for that is, of course, what? Shielding effect. And let's take an example and see about this. Let's take an example. And if you actually see, take the case of the first group, that's better for you. If you look into the lithium, this is the nucleus of the lithium. And if I write the configurations, it is 1s2, 2s1, right? And between the nucleus and the outermost shell, you have only one subshell. That is, the electrons occupy, yes, you can see the electrons are occupying S. And when I say S, between the nucleus and the outermost shell, bulk of the electrons are added toward S subshell. And you must understand S is a better shielder. S shields better because S is symmetrical around the nucleus. It is non-directional. You find the electron density evenly distributed around the nucleus. Right? Also considered to be non-porous. So, it is a better shielder. Right? So, it's a nuclear force of attraction which is supposed to fall here. This seems to be shielding, and this is a good shielder. Right? Similarly, if you take sodium, and this is the nucleus of sodium, then the configuration is 1s2, 2s2, 2p6, 3s1. You must understand. Right? So between the nucleus and the outermost shell, you have the electrons occupying two subshells, the electrons in S and P. And both are good shielding. Both are good shielders. Right? And then come down to rubidium and cesium. Rubidium and cesium between the nucleus and the outermost shell. Right, this is 4, 5s for rubidium and 6s for cesium. Between these two, the bulk electrons, are added to D and F. You must understand. For rubidium and cesium, between the nucleus and the outermost shell, the number of shells increase, but the bulk of the electrons are added to D and F, and these are bad shielders. These are basically what? Bad shielders. That's why you see the sizes of lithium, if I give an arbitrary value of 1 angstrom, then for sodium it becomes 1.5 angstroms. For potassium it is becoming 2 angstroms. And then for rubidium and cesium, if you see, it is 2.1 and this is 2.12. You can see the way the size is increasing at the top of the group, whereas when you come to the bottom, that same thing decreases. The magnitude will be what? Decreasing. The magnitude of increase decreases. I'm not telling the size is decreasing. The size is increasing. You can see from 1 it has become 2.1. The size is increasing because the number of shells go on increasing. But it also matters the electrons are occupying which subshells, where S, P, D, F. If the bulk are occupying D and F, then you're a bad shielder. So you don't expect the same increase in size which you actually see it at the top of the group, because in top, the bulk of the electrons are added to what? The S subshell or the P subshell, which are better shielders. So shielding effect, of course, is extremely important. It's very, 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 very what? Important thing you must understand, right? That's application number 1, which I was telling you. That's a question in exam. Shall I read the question once? Yes, down the group, the size increases, but the magnitude of increase which is seen at the top fades down the group. It fades down the group. You must understand that, right? If that is the case, then let's take application number 2. Watch carefully here. Watch carefully. Let us take an application number 2. And remember, please bank on it. Application 2, and please bank on this question. Please bank on this question. This is 100% sure in exam. This is 100% sure in exam. 100% sure in exam. Right? Please bank on this question. What is this question is, right? The ionization potential values are basically indicative of the valency of a particular what element. Try and understand what I'm telling. The ionization potential values are indicative, are the index, or I can say it is an index. The ionization potential values are basically index of valency of a particular element. In our simplest language, if you wanted to tell me, then seeing the ionization potential value, I can judge the valency of an element. I can judge the valency of an element, or the group number of an element, or the group number of an element. Remember, number of valence electrons is nothing but the group number. So the total number of electrons that are present in the outermost shell of an element indicates its group number. For example, lithium has the number of electrons in the outermost shell to be 1. So it belongs to first group. Beryllium will be having 2 electrons in its outermost shell, so it belongs to second group. Aluminium will be having 3 electrons in its outermost shell, it belongs to third group. Carbon has 4 electrons, so it belongs to the fourth group. Similarly, total number of electrons that are present in the outermost shell indicate the group number of that particular element. You must understand that. Right? So, there is a link between ionization potential values and the number of valence electrons, and hence the group number. Remember that the ionization potential values reflect on the number of valence electrons that are present in the outermost shell of an element, and that also indirectly is telling you that it's a group number, right? So what I mean, I just write it here. Ionization potential values of an element, I would like to underline, IP values of an element reflect on number of valence electrons. IP values of an element reflect on the number of valence electrons, and hence group number. And hence group number, you must understand. So IP values of an element are index of what? Group number. You must understand this. Well, I'll catch hold of this and hence the question. And hence the question. And hence the question. So, if I can write the question for you, here is the question. Observe carefully. Here is the question. And the question is, watch. The following are, I draw the attention of everyone, please. The following are the ionization potential values of an element M. The following are the ionization potentials of an element M, right? And he is asking, find one, formula of the oxide of the element. 2, formula of chloride of that element. 3, the formula of nitride of that element. He is given the values of ionization potentials of a particular what? Element, and he is asking you to write the formula of the oxide, formula of the chloride, formula of the nitride. That's the question. Now, how do you do that? Well, I told you, IP values of an element reflect on the number of valence electrons. Number of valence electrons. Once you know the number of valence electrons, then I think you know the group number. And once you know the group number, then I think we will be in a position to find out the formula of oxide, chloride, or what? Nitride, that's for sure. And it is no problem in determining that. You must understand that. Right? So what are the values given? The values given are like this. The IP values are the first ionization of M, this particular element M, right? The first ionization potential is 20 electron volts. That means the first electron that is removed from the outermost shell required 20 electron volts energy to extricate it, to kick it out. And remember, ionization potential, if you recollect the definition, you have done some work. You have done some work in bringing this electron from infinity to a point where the nucleus is now holding. And in the process of bringing this electron from that point to a point where the nucleus is holding, you have spent some energy. So same energy someone should be giving to kick it out. So that is 20 electron volts, you must understand. That is the first ionization potential. That means energy required to remove the first electron from the outermost shell. It's 20. The second ionization potential is going to 48 electron volts. And the third ionization potential is coming to 90.3 electron volts. No, not 90.3. Rather, this is 121.2 electron volts. These are arbitrary values. Arbitrary values. Right? And even the fourth ionization potential seems to be 700 electron volts. Well, first of all, looking at these ionization potential values, I'm not surprised. I'm not surprised. Why I'm not surprised? Because you look into this, if this is the element M, and if you try to remove the first electron, it develops a unit positive charge. And from this positive charge, if you try to remove another electron such that you get double positive, it is difficult for you. This is if it is I1, it would be further difficult, which is I2, and I2 will be greater than I1, because whenever you try to remove one electron from the outermost orbit of an element, then the atom shrinks in size. And for shrinked size, again, if you try to remove one more electron, it becomes further difficult for you. So I2 is very much greater than what? The first ionization potential. So the second ionization potential is always greater than what? The first. Now coming to the third, if you try to remove one more, and if you want it to become +3, an electron, I3, then I3 will be greater than I2, which is greater than I1. Because whenever you remove one electron from an atom, the size shrinks. It's almost like 10 people, 10 idlis. 10 people, 10 chocolates. 10 people, 10 chocolates. Each one will get one chocolate. Suppose if one person is dead, then the number of chocolates people get will be more than one. Suppose if the other fellow is also dead, then the quantity of chocolate increases for the remaining 8 people. Similarly, if you have 10 electrons and 10 is a nuclear force, then all the nuclear force is evenly distributed for 10 people. Suppose if you remove one electron is dead, then the same nuclear force is now distributed for 9 people. Then the outermost shell is pulled inwards because you have greater force of attraction. If you remove one more electron, then the same nuclear force of attraction is now distributed among 8. Then the outermost shell is pulled further inwards. So whenever you are pulling one electron, then it is difficult for you to remove the electron from that, and that's why the third ionization potential greater than the second, greater than the third, greater than the fourth, you must understand that. So that is how the trend is. That's why I say I am not surprised at all with these values. So come back to the question. What is the question? Ionization potential values of an element reflect on the number of valence electrons and hence group number, and there is a question on it. Look into the question here. The following are the ionization potential values of an element. He is asking the formula of oxide, formula of chloride, formula of nitride. And here are the ionization potential values what he has given. First IP 20, fine, fine. Second IP 48, absolutely fine. Absolutely fine. Because removing the second electron is difficult. It is difficult because the size of the element has shrunk. Fine, so 48.5, fine. Sounds normal. Sounds normal. From 20, if it is 48, it's a struggle. It's a struggle. Of course it's a struggle, but I'm not surprised. I'm not surprised. And then the third one, where you have 121. Fine. Fine, fine. Because once you remove 2 electrons, you're further shrunk. You're further shrunk in size. And if you're further shrunk, removing the third electron would be extremely difficult for you. So you started off with 20, 48, no surprise. I'm not surprised. Then you came for 121. I'm not surprised. Because the third would be difficult for you. The third will be difficult for you. And then, now I have an issue. Now I have an issue. You look into the value. Well, 20 to 48, fine, legitimate. 48 to 121, legitimate. But it's no legitimate when someone is kicking from 121 to 700. 700 is not legitimate. Not legitimate. I can understand a jump from 20 to 48, fine. From 48 to 121, fine. From 48 to 700, no, not fine. Not fine. It is not fine. This seemed to be not legitimate, but rather it seemed to be absolutely abnormal. It's abnormal value. It's abnormal value. Why such an abnormal value has come into place? First of all, in the first place, let us discuss. So, this is normal. This is also normal, but this seemed to be absolutely abnormal. Absolutely abnormal. If I put this into a graphical representation, watch carefully. Here is a graph. You must understand. Here is a graph for it. If I plot the ionization potential values on the y-axis, then look into this. And this is right IP values versus energy. This is the element 20. How much is that? 20 electron volts. And then it increased to basically 48.2 electron volts. Fine. This further increased to 121. And this seems to be absolutely abnormal. This seems to be straight now. This is 700. Till here, it seemed to be normal values. This, I consider this to be a huge jump. Huge jump, which I disagree. Something happened. Legitimate, yes. To remove the first, you spend 20. For the second, it is 48, legitimate. Third, it is further difficult. It is 121. Fine. But 700, something happened. It's abnormal. And I consider it's no increase. Rather, it's a jump. It's a jump, you must understand. It's no increase of ionization potential, but rather it's a jump. Why such a thing should happen? Let's have a pictorial representation of why and why that has happened. You must understand. Let us see this. Let us see this. This is the nucleus of a metal M. Right? This is the nucleus of the metal M. This is the first shell. This is the second shell, assume. And this is the third shell. And this is the outer shell, let us say. This is the outer shell. Outer shell. Now, here is one electron, here is another electron, here is another electron. 3 electrons. And now, to remove the first electron, to remove this, you spent 20 electron volts. 20. Because it is held by the nucleus. You need to spend some energy to remove it. Then, after removal of that, removal this, difficult. And you spent 48. Whenever you are removing 1111 electrons, the outermost shell is going close towards nucleus. Shrinking. And the third electron to remove, this is further difficult. And this is 121 electron volts. It is 121 electron volts. You must understand. Further decreased. Further close is what? The outermost shell towards nucleus. So it is difficult. Right? And now what happened? You have electrons here also in the first and the second. That is the outermost shell which I am speaking of. And now what happened? You attempted to remove the fourth electron. You attempted to remove what? The fourth electron. When you try to attempt to remove the fourth electron, there are no 4 electrons here. There are only 3. But the fourth electron, this is the fourth. That means that after you finish the outermost shell vanished. The outermost shell vanished. When it's vanished and you enter the fourth shell, that means you are further close to the nucleus. Look into this. This is closer to the nucleus. It's closer. Then it becomes for you extremely difficult. That is the reason why you find a jump. 700 electron volts. 700 electron volts. It's a jump. It's an abnormal value indicating. So what does it indicate? What does this indicate? It indicates, I would like to write it. Well, I would like to write it rather. Remember, number of normal values. Now, what are the number of normal values? 1, 2, 3 without any surprise. Is nothing but number of valence electrons. That is nothing but the number of electrons that are present in the outermost shell. Which is otherwise, it's nothing but group number. Number of normal values is equal to number of valence electrons, which is nothing but what? Group number. It's nothing but group number. So, look into this. Let's apply this to here. This seems to be normal. This also seems to be normal. This also seems to be normal. I am not surprised with those values. But between the third and the fourth, there seemed to be a jump. There seemed to be a jump. That's abnormal. So, number of normal values are 3. I think you'll agree. 1, 2, 3. So, number of valence electrons are 3. So, group number is 3. It implies the element M belongs to the third group. It belongs to the third group. It belongs to third group. And if you can recollect any element which you know in the third group, then if M belongs to third group, let's take the case of aluminium, which belongs to the third group. Third group element, the best known element for you in the third group is what? Aluminium. Can't you write the formula of oxide of aluminium? Yes, it is Al2O3, and for this question, the formula of the oxide is M2O3, bauxite. Second is asking formula of chloride. Well, you know the formula of chloride of aluminium is AlCl3, so it is nothing but MCl3. Now he is asking formula of nitride. Well, if that is the case, then it is aluminium nitride looks like this, ALN. Because ALN, because it is Al plus 3, it is basically Al plus 3 and N minus 3. This is the combination. So in general, it should be Mn. It is Mn. I got the answer. I got the answer. So the answer for oxide, this is M2O3, MCl3, and this is Mn. You must understand. You must understand that. So what I mean is the ionization potential values are indicative of number of valence electrons. That is, number of electrons that are present in the outermost shell of an atom. If you know the number of valence electrons, then you know the group number. Once you know the group number, can't we find out the aluminium or the whether it's oxide or chloride or the nitride formula? Of course, yes, we can. Well, I would like to practice one more question on this. How to judge normal values, legitimate values, how to judge a jump. We would like to practice one more. Let us see. Well, I would like to rub this. Watch carefully here. Here is a question. The ionization potential values of an element M are, the first ionization potential is 16 electron volts. 16 electron volts. The second ionization potential is of 36.8 electron volts. And the third ionization potential seems to be 291 electron volts. And he wanted now write the formula of 1 oxide, 2 nitride, 3 fluoride, oxide, nitride, and what? Fluoride of that particular element M. Since we know the subject points, let us have a closer look on the values. The first value, 16 electron volts, seem to be absolutely normal. It's normal. Energy required to remove the first electron from the outermost shell is 16. Normal. Second, 36.8, fine. Normal. Second, I struggled. For the second one, I struggle, and it's normal. But the third one seemed to be abnormal, and I call this to be jump. And if you look into the graph of this particular element, then the first is 16, then it is increasing to what? 36.8, and then sudden there is a linear increase. Well, this is a jump. That is 291 electron volts. That's a jump. So these two I consider to be normal. And as we know, number of normal values Number of normal values are 2. So group number is also 2. So then if the element is M, belong to the second group. It belongs to the second group. So group number is 2. Group number is 2. And then you have your element M belonging to the second group. Let's take second group element to be magnesium. And if you want the oxide formula for magnesium, it is MgO. If you want nitride, it will be Mg3N2. It's Mg3N2. And then for the fluoride, I think you have magnesium fluoride. And for the metal M, you can write MO, M3N2, and then it is MF2. You must understand, MF2, right? So this is nothing but M plus 2 and O minus 2. This is 2M plus 2, right? 3M plus 2 plus and 2N minus 3. You can actually see this is 6 and 6, it's neutral. And then it is M plus 2 and 2F minus. You can understand here, that's how it is split. So the formula of the oxide is MO, nitride is M3N2, and the fluoride formula is MF2. You must understand this. So number of normal values, understand? Number of normal values is nothing but what? Number of electrons that are present in the valency shell. And number of normal values is nothing but valence electrons. That itself is group number. Once you know the group number, you will be in a position to find out oxide, nitride, or what? Fluoride. You must understand. Right? That's application number 2. Let us go in for application number 3. Shall we? Observe. Right. Application 3. The shielding effect is pronounced more in the F subshell. The shielding effect is more pronounced in what? F subshell. And you will get a question on this. You'll get a question on this. And I can say this question you can bank upon, and this is 100% sure. This question you'll get it in exam for sure. You'll get in the exam for sure. The more pronouncing shielding effect is a question in exam. And why it's pronounced in F subshell? Because F is a poor shielder. It's a poor shielder. It's a poor shielder. Very poor. And if someone is asking me why, then they say F has a peculiar diffused shapes. They have a peculiar diffused shapes. When you say I have peculiar diffused shapes, it implies that F subshell has holes. The F subshell has what? Holes. So, nuclear force of attraction penetrates. It basically what? Penetrates through that holes which are given. They are penetrating towards the holes. Thereby, nuclear force of attraction penetrates, resulting in increased force of what? Attraction. Increased force of what? Attraction, thereby resulting in decrease of size. Thereby resulting in what? Decrease of size. You must understand. No one knows the shape of F orbital. You know the shape of F, it is spherical. You know the shape of P, it is dumbbell. You know the shape of D, it is double dumbbell. But if you ask you F, no one knows. They simply tell you they have a peculiar diffused shapes. It is eightfold degenerate. Eightfold degenerate is difficult for you to visualize unless you put it in a computer. But one characteristic which we know is basically it has a very peculiar diffused shapes. That means that the F shell has pores. So if the electrons are present in F, they have pores, then the nuclear force of attraction is basically penetrating through the pores and falls on the outermost shell, which results in what? Pulling towards inwards, thereby the size decreases. Where do we find such a thing in periodic table? Where it is greater noticeable, this philosophy what we are telling is a question in exam and you can bank on it. You can basically bank on it. So where does this entire philosophy, what I'm telling, where it's a question also it is sure, where do we find it? Where do we find it is the issue. Where do we find it is the issue. And remember, if you look into the periodic table, look into this. To the extreme left, you have first and second groups. To the extreme right, you have 8 groups, six groups. And in between, you have D block. This is S block. This is P block. S can accommodate 2. P can accommodate 6. This can accommodate 10. So 10 plus 2 is 12 plus 6, 18 groups. And other than this, from the mainframe, there are 2 series which are kept here. That is the F block. This entire thing together, this I call F block. They are removed from the mainframe of the periodic table and put it down to maintain the decorum of the periodic table. F block. And this is called the 4F series and this is called the 5F series. 4F and 5F. You must understand. Now these together, right, the 4F, we call this to be lanthanides. And these are called the actinides. Those are called the actinides. And this starts from cerium to lutetium. Cerium to lutetium. And it is 58 to 71, total of 14 elements. And the 5F series is from thorium to lawrencium. Thorium to what? Lawrencium. And it is 90 to 103. Again, it is 14 elements. You must understand. So, in the mainframe of periodic table, you have 18 groups. But at the bottom, they are removed from the main group and put it as a different block, that is F block, because the bulk of the electrons are now getting into the F subshell. The bulk of electrons are now getting into the F subshell. And the first series, this is called actinides. So sorry, the first series is lanthanides, which starts from 58, ends at 71. So the total number of elements, if you see, 71 to 58 is 13, 13 plus 1 is 14. And F can accommodate 14 electrons, so hence it is called the 4F subshell. Similarly, you have 5F, which is actinides, which starts from 90 to ends at 103. 103 minus 19 is 13, plus 1 it is 14. That's how we calculate the total. Final minus initial plus 1 is always gives you the number. Must understand? So the entire periodic table, the F block is put separately to maintain the decorum of the periodic table, the F subshell. And we know great features of F. We know the philosophy of F. Whoso enters in F, what happens we know. What is that we know? We know that it's a poor Schilder. It's a poor Schilder. And why it's a poor Schilder? It has a very peculiar diffused shapes. They don't know the shape of F orbital. Now, people might ask me, Why are you telling that they don't know the shape of F orbital? That's a question many people wanted to ask me. Well, first of all, understand F subshells means you're actually far away from the nucleus. You're not there at first, second, third, fourth. It all starts from fifth and the sixth. It all starts from sixth and seventh rather. Sixth period and the seventh period. Sixth period is almost far away from the nucleus because after all you have 7 periods. When you are actually far away from the nucleus, the energy is too high for that electron. And if you wanted to have a picture of the F orbital, then you have to pass radiation which matches with the parameters of that electron energy, which is high, which is very, very high. So if you attempted to do it, the radiation which matches with the energy of what? The electron, which is already high, if you try to put that radiation onto the electron, forget about getting the photograph, the electron will run away. You can't get a photograph out of it because the electron's energy is too high to get a photograph. So it was told that it's an 8-fold degenerate and has a peculiar diffuse shape, and the effect of this poor shielding effect, you get it falls in lanthanides and actinides, and you have a question on that.